Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. In this lab, we will review some of the concepts relating to MSS that we covered in the previous video. First, let's look at the IP info in the lab notes. This topology is similar to the one in the lecture video. Just be aware of the IP addressing, it's a bit different. There is a GRE tunnel between R1 and R2 over the ISP infrastructure, which is represented by this single ISP router. Now let's get right into the lab instructions. The first step says to initiate a TCP connection using SSH from R1's Tunnel 0 interface to R2's Tunnel 0 interface. Note that there are passwords on the devices. The router logins are Jeremy and CCNP, and the enable secret is CCNP. The instructions say to use a debug to verify the MSS for the connection, as well as a show command. It then asks why the MSS is neither the default of 536 used for remote connections or 1460 used for local connections. Remember, a Cisco iOS device will by default use an MSS of 536 when connecting to a device in a remote network, and an MSS of 1460 when connecting to a device in a local network. However, those values only apply to connections to or from the router itself, not connections going through the router, for example when Server 1 connects to Server 2. Server 1 and Server 2 are Linux servers, not Cisco iOS devices, so they will use different default values. Now let's go on R1 and try that first connection. First I'll use enable, and then enter the password of CCNP, all lowercase letters. Now before initiating the TCP connection to R2, I'll use a debug command. Debug IP TCP transactions. This will display information about the TCP connection between R1 and R2. Now let's initiate the TCP connection. SSH-L Jeremy, that's how I specify the username to use for SSH, then 192.168.12.2, R2's Tunnel 0 IP address. Okay, so a series of debug messages are displayed, as well as this login banner. I'll enter the password of CCNP. Now let's look at the debug messages. The MSS is displayed up here. Connection to 192.168.12.2, port 22, advertising MSS 1436. And then below it, peer MSS is 1436, MSS is 1436. So, R1 and R2 are not directly connected physically, so you might expect them to use an MSS of 536. However, because they are directly connected virtually via the GRE tunnel, the MSS they use is based on the default for direct connections, 1460. However, the MSS they actually use for this connection is not 1460, but rather 1436. Why is that? It's because they both know this connection is using a tunnel interface, so they automatically subtract 24 bytes for the GRE and IP headers, resulting in an MSS of 1436 bytes. Now let's use a show command to verify the MSS. Since I'm already logged into R2, I'll view it here. First I'll use enable, and then enter the password of CCNP. The command to view information about active TCP connections is show TCP. This command can take a bit of time to display, so wait 10 seconds or so. Note that this command displays a lot of detail about each active connection on the router. If you want to view a summary, you can use show TCP brief, but that doesn't display the information we want now, the MSS. So, towards the bottom of the output of this command, you can find the MSS. It says max data segment is 1436 bytes. That's the MSS both routers will use for this connection. Okay, we're done with step 1, so I'll use exit to end the connection for now. Now let's return to the lab notes for step 2. It says to configure the MSS for TCP connections to and from R2 to use an MSS of 1400. We looked at that command in the lecture video. It's IP TCP MSS. Then we'll do step 3 after it, which says to initiate a TCP connection using SSH, again from R1's Tunnel 0 to R2's Tunnel 0 interface. Okay, let's do step 2 first. I'll directly access the console of R2, use enable, and enter the password of CCNP. The command is done from global config mode, so conf-t. Now let's configure it. IP TCP MSS 1400. That's it. Remember, this command applies only to TCP connections to and from R2. For example, when connecting to R2 using SSH. It doesn't apply to connections that go through R2, such as when server 1 connects to server 2. Now let's do step 3 and initiate that TCP connection from R1 to R2 again. Same as before, SSH-L Jeremy 192.168.12.2. Okay, just like before, we get a series of debug messages. I'll enter the password CCNP, and let's look at those debugs. So, up here it says advertising MSS 1436. So just like the first time, R1 says its MSS is 1436 bytes. However, down here it says peer MSS 1400. MSS is 1400. So R2 then advertises a lower MSS, the 1400 byte MSS we just configured, and the final MSS is 1400 means that R1 accepted that lower MSS value, and both R1 and R2 will send maximum payload sizes of 1400 bytes. Let's confirm that with the same show command again. Enable, password CCNP, and the command is show TCP. While we're waiting for that command to display, let me show you a statement from RFC 879, an old RFC from 1983. Let me read this part of section 3. This MSS announcement, often mistakenly called a negotiation, is sent from the data receiver to the data sender and says, I can accept TCP segments up to size X. The size may be larger or smaller than the default. The MSS can be used completely independently in each direction of data flow. The result may be quite different maximum sizes in the two directions. This quite clearly states that a different MSS value can be used in both directions. So in this case, R1 advertised an MSS of 1436, and R2 advertised an MSS of 1400. That means R1 would send segments to R2 with a max payload size of 1400 bytes, and R2 would send segments to R1 with a max payload size of 1436 bytes. However, if you look at the information here on the right, you can see this RFC is designated as historic, and it is obsoleted by RFC 9293, which I'll click on now. RFC 9293 is the latest RFC defining TCP, and it was actually released in August 2022, so it's quite recent. I'll scroll down to the table of contents and click on 3.7.1, the maximum segment size option. I won't read through this section, but basically it states that the lower of the two MSS values should be used, instead of a different MSS value being used in each direction. This section is a bit difficult to read, and it requires that you reference some other RFCs to really make sense of it. But don't worry, you don't have to understand this much detail for the CCNP. Instead, we can just confirm the actual behavior of Cisco devices. No need to read all of the theory. Let's go back to the lab, and now view the rest of this command. Note that it says, max data segment is 1400 bytes. R1 and R2 each specified a different MSS value, but they both ended up using the lower value, 1400. Okay, I'll use exit to close the connection. So remember that if each device specifies a different MSS value, Cisco iOS devices will use the lower of the two values. Other devices may behave differently, but since this is a CCNP course, we'll just focus on how Cisco iOS devices behave. Now let's return to the lab notes for Step 4. Step 4 says to initiate a TCP connection from Server 1 to Server 2. We should use a packet capture on the Server 1 to R1 link to verify the MSS for the connection. By now, you should know how to do a packet capture in CML, so I won't show it here. I've already got a packet capture ready that I took before. Note that, as always, I will include the packet capture with the other lab files. Step 4 also asks what message R1 sends to server 1. So let's initiate that connection from server 1 to server 2. I'll go on server 1. The login is Cisco, and password Cisco. That is the default login for the Alpine Linux node in CML, by the way. So let's SSH to server 2. SSH-L Cisco 192.168.2.10. And the password is Cisco. Okay, we're in. Now we don't actually need to do anything on server 2, so I'll exit out. Now let's check that packet capture I prepared beforehand. So, messages 3 and 4 are the SYN and SYN-ACK exchange. Note that both server 1 and server 2 specify an MSS of 1460 bytes. Okay, now look at the message with the green text from R1, 192.168.1.1 to server 1, 192.168.1.10. It's an ICMP fragmentation needed message. Server 1 and server 2 don't know that their connection goes through a GRE tunnel, so they first assume an MSS of 1460 bytes. Then, in message 10, server 1 tries to send a message to server 2 with the full TCP payload size of 1460 bytes. Note that in the length column here in Wireshark, it says 1514 bytes. That is 1460 bytes for the TCP payload, plus 20 for the TCP header, plus 20 for the IP header, plus 14 for the Ethernet header. Note that the length values in Wireshark include the Ethernet header, but not the trailer. If the trailer was included, it would be 1518. Now let's open up the IP header of that message. In the flags field, note that the bit pattern is 010. That second bit, the don't fragment bit, is set to 1. As I mentioned in previous videos, end hosts such as Windows PCs, as well as these Linux servers, use path MTU discovery by default. That means they set the DF bit on their IP packets by default. And if they get an ICMP fragmentation needed message, they adjust their message size down as needed. So, because the DF bit was set, R1 dropped message 10 and sent the fragmentation needed message to server 1, message 12 in this packet capture. Let's examine that fragmentation needed message. Open up the ICMP contents of the message and look at the MTU of next hop value. It tells server 1, in order for me to forward this packet, it has to fit into the MTU of 1476. Remember, GRE tunnels should use an MTU of 1476, 24 less than the Ethernet default of 1500. Likewise, the MSS of TCP connections that go through the tunnel should be 24 bytes less than the default of 1460. Notice that after that one fragmentation needed message, there are no more in this packet capture. Although server 1 first decided on an MSS of 1460 bytes for this connection, thanks to that fragmentation needed message from R1, server 1 learned that it should actually use a lower MSS, 1436 bytes. Okay, let's return to the lab notes. Step 5 says to terminate the TCP connection from server 1 to server 2 and initiate a new one. We should then use a packet capture again to verify the MSS for this connection. Again, I have already prepared a packet capture, but I will go back to server 1, and then I will use the up arrow to return to the previous SSH command and connect to server 2 again. Password Cisco. Now let's examine the packet capture for that connection. I recommend taking your own packet captures, but feel free to just look at my packet capture if you prefer. This time in message 2, look at the MSS server 1 specifies for the connection. It learned from the previous connection with server 2 that this connection should actually use an MSS of 1436 bytes, not 1460. Interestingly, server 2 in message 3 still specifies an MSS of 1460 bytes. That's because it never tried to send a message that was too large, and never received a fragmentation needed message. Okay, that's all I wanted to point out, that thanks to path MTU discovery, server 1 was able to adjust its MSS when communicating with server 2. So even for this new connection, Server 1 knew to use an MSS of 1436 bytes. Now let's return to the lab notes. Step 6 says to disable ICMP unreachable messages on R1G01. Fragmentation needed is a type of unreachable message, so this will prevent Server 1's path MTU discovery from working. Path MTU discovery relies on ICMP to function, but often ICMP messages may be denied, for example by a firewall in the traffic path, so path MTU discovery doesn't always work. By disabling ICMP unreachable messages on R1's G01 interface, we will simulate a firewall denying that ICMP traffic. Now, before actually doing the configuration, I will also do step 7, which says to shut down and power on Server 1 and Server 2 to clear their caches. So I'll just hover over Server 1, hit the stop button, and then power it on again. I'll do the same on Server 2, although since we're focusing on Server 1, it's not actually necessary in this case. Okay, while Server 1 and Server 2 are booting up again, I'll go on R1 and disable ICMP unreachable messages on G01. First, enter global config mode with conf-t. I need to configure the command directly on the interface, so interface G01. First, let's check that ICMP unreachables are enabled. Do show IP interface G01. Here it says ICMP unreachables are always sent. As you saw earlier, R1 sent an ICMP unreachable message to Server 1. So let's disable them. I didn't show this command yet, but if you tried this lab yourself before watching the video, I hope you were able to do a Google search to learn it. As I've said before, Google is an important skill for anyone in IT. The command is no IP unreachables. Let's confirm that it was disabled. Do show IP interface G01. Okay, it says ICMP unreachables are never sent. Perfect. Now let's return to the lab notes. Step 8 says to once again initiate a TCP connection from Server 1 to Server 2 and use a packet capture to verify why SSH doesn't work this time. Again, I won't do the packet capture this time since I already prepared the pcap file and you already know how to do packet captures in CML. So I'll go on Server 1, which has booted up again. Then log in with username Cisco and password Cisco. SSH-L Cisco 192.168.2.10. This time, nothing happens. Server 1 is trying to set up an SSH connection with Server 2, but it's not working. Eventually, you'll get a message saying the connection is closed, but I'll just use Ctrl-C to end it. Now let's look at the packet capture I prepared. So in messages 4 and 5, we have the TCP SYN and SYN ACK between Server 1 and Server 2. Because I rebooted Server 1, it no longer remembers that it should use a TCP MSS of 1436 bytes when connecting to Server 2, so it specifies an MSS of 1460. Note that the TCP connection was established successfully, since no large messages are sent in the three-way handshake. However, the SSH connection itself was not able to complete. Look at message 12. Server 1 once again sends a message with a length of 1514 bytes. Remember, that length includes everything except the Ethernet trailer. Last time, R1 dropped the message and sent an ICMP fragmentation needed message to Server 1. However, this time, R1 does not send that message. So, Server 1 never learns that it should actually use a lower MSS for this connection. It keeps retransmitting that same TCP segment, as indicated by the TCP retransmission statement here. However, R1 keeps dropping the messages because they exceed the MTU. Finally, at the bottom of the capture in message 70, Server 2 sends a TCP reset message, as indicated by the RST here. Reset is one of the TCP flags like SYN and ACK, and it can be used to terminate a connection. Basically, Server 2 gets tired of waiting for a message from Server 1 and tells Server 1 that the connection is finished. So, since R1 cannot send ICMP fragmentation needed messages, Server 1 kept trying to send TCP segments that were too large, and the SSH connection could not complete. Now let's return to the lab notes. Step 9 says to configure R1's Tunnel 0 interface to adjust MSS values to an appropriate size. And then in step 10, we will once again initiate a TCP connection from server 1 to server 2. Then we will look at debug messages on R1 to verify that it adjusted the MSS values. So I'll go on R1. We should configure MSS adjustment on the Tunnel 0 interface, so interface T0. Let's configure it to adjust MSS values to 1436, since that's the largest MSS value that will work over the GRE tunnel. The command is iptcp adjust MSS 1436. Okay, now before trying the connection, let's use end to return to privileged exec mode, and I'll start the debug. To view debug messages related to TCP MSS adjustment, the command is debug iptcp adjust MSS. Okay, now I'll go to server 1 and try to SSH to server 2 again. It should work this time. SSH-L Cisco 192.168.2.10. Okay, this time we get the password prompt, and server 1 is able to connect to server 2. Let's go back to R1 and check the debug messages. First, I'll use undebug all to stop the debug messages. So in this debug message here, it says original MSS equals 1460, adjusted MSS equals 1436. So it adjusted the MSS server 1 specified to server 2. Then it once again says original MSS equals 1460, adjusted MSS equals 1436. So it also adjusted the MSS server 2 specified to server 1. Because the MSS value is now appropriate, the SSH connection between server 1 and server 2 was successful. Okay, that's all for this lab. In this lab, we reviewed some of the MSS concepts covered in the previous lecture video. As always, make sure to spend some time experimenting with MSS on your own. You can use this lab topology here to experiment, or make your own lab. Either way, it's important practice. I hope this video was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Yonatan Makara, Velva Jacob, George Streeter, Funny Dart, Nasir Chowdhury, Devin Suku, Gustavo BR, Gerard Baker, Marcel Lord, Pavel M., Mr. Erlison, Dragos Hirnea, Zakib Shah, Mir Salman, Mazen Anderson, Vitaus194, Gina Lindley, Nehemia, Justin Watke, Mark Jackson, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector Hernandez, Ali Polat, Maratuba, Roji Kuriakos, Arpad Konives, 5 Feet, Daniel Brown, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yavuz, Samuel Tavares, Mustafa Ersoy, Dear Diso, Nasser Zahar, Alexandru Badic, Brian Grant, Georgi Gemejev, Ahmed Ismail, Dibya Swain, Tan No, Arlen Plagaria, Adelson Pereira, Abdo Zizo, and Farad69. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.